In this problem, we have an electromagnetic wave that comes and hits a charged particle. And so let's draw our electromagnetic wave really quickly. So I'm going to have the electromagnetic wave come in this way. And we know that the electric field will make it polarized in the z direction. So the electric field is going to look like this. And the magnetic field, then if we're moving in that direction, K, which is in the positive y direction, N, then the magnetic field will be in this direction. And so we have our electromagnetic wave. It is going to come and it is going to hit a charged particle, a charge Q. When the wave hits, when this part of the wave hits, it's going to apply a force that tends to make the particle go down. When this part of the wave is hitting, it's going to apply a force that tends to make the particle go up. And when the particle is in motion, if it is moving due to this applied force, then the magnetic fields will themselves apply a force on the particle. For the problem, what we're going to do is we're going to assume that the electric fields are much more dominant in what they're going to do to the particle, and they drive the motion of the particle, and then the magnetic force can be a result of that driving, but it's not really going to change the motion because it's going to be so much smaller. If you're wondering why it's going to be so much smaller, it's because of that 1 over c in the relationship between the electric and the magnetic fields in an electromagnetic wave. And so we're dividing essentially by a factor of v over c, and let's say the particle is moving quickly, at a kilometer a second, that's 10 to the 3 meters per second, then this v over c factor that's going to make the magnetic force smaller is still 10 to the 5 smaller. And so it's not really going to contribute. And so that's why we neglect the magnetic field when we find the motion of the particle. Anyways, let's get started. For part A, find the velocity of this particle as a function of time. And so what we're going to do is we're going to find the force. Force electric is equal to QE, but E, right, is equal to Q E naught times cosine of omega t. We're gonna say this particle is at x equals 0, or is at the origin. That way we don't have to worry about the spatial component there, because anything dot 0 is 0, so we don't have to worry about the spatial component. Now, how do we do this? Well, we use Newton's second law, and we say that the second time derivative, mass of the particle, times the second time derivative of its position is going to be equal to what we have here, Q E naught cosine of omega t. Now, in order to solve this type of problem, usually you break it up into a homogeneous part where you set that equal to 0. You find that. What we find here is that x of t will have these two unknowns, ax plus b, or at plus b, which means that it can be moving, it can be located anywhere, and it can be moving with constant velocity, and it won't make, and this won't change that part of that. That's what this solution says here. For ease of use here, we're just going to say that this is 0, and that we're looking at a stationary charge, so that that homogeneous solution we're just going to say is 0. And then we look at the inhomogeneous solution. For the inhomogeneous solution, you make a guess of what it should look like, and then you plug it in. And so what we're going to guess is we're going to say that this is going to have that same structure. It's going to have a cosine. So we're going to say A times cosine of omega t, like that. And then we're going to plug this in. The second, if I take two derivatives here, I'm going to get a minus omega squared come out front. And so plugging that in here, I'm going to get minus omega squared m times a cosine of omega t will be equal to q e naught cosine of omega omega t. And now I can solve for that unknown a. And so I can say in this part that x of t is going to be equal to minus q e naught over m omega squared cosine of omega t. And so this is the position of the particle. If I want the velocity, I have to take the first derivative, right? So x dot as a function of t is going to be q e naught over m omega sine omega t. And so that is how you solve that type of problem mathematically. Let's move on to part B. Part B says show that the time average of the magnetic force is equal to 0. And so we need to write down what the magnetic force is. And so B, the magnetic force, is equal to Q x dot across the magnetic field. Well, luckily for us, this x dot is in the z hat direction. I didn't write that down. I should probably do that now. These are vector x's, and this is in the z hat direction, and z hat direction. And so I can carry this out. If I do z hat, the B field we've already determined is going to point in the x hat direction, and so the force will point in the y hat direction, or in the minus y hat direction in this case, but yeah, the minus y hat direction, that'll work. So let's get going. So the magnetic force is equal to the B, right, is E naught over C, that's the magnitude, and then that same cosine. And so Q E naught over C. The x hat, we can write this down. This is Q E naught over M omega. And then we have sine of omega t. Then we have the direction, which is z hat cross the B is in the x hat, and so this will be in the y hat direction. That's it. And so the time average is going to be this, but the time average of the sine. So q squared E naught squared over mc omega, and the time average of the sine function. But a time average of a sine function is 0. It's above the line as much as it is below the line, so the time average of the magnetic force is 0 in this case. Okay. So we've shown that. Now let's go to the final problem. We're going to redo this, but we're going to put in an additional damping force. F is equal to minus gamma V, or minus gamma x dot, whenever we do the problem. So, again, copying some of what we have from above, we are going to get that m d squared x over dt is going to be equal to q e naught cosine of omega t, that's from there, but minus gamma m times dx over dt. And so all I did is I wrote down Newton's second law when applied to a particle with a time-varying electric field due to a plane wave coming by, and some external damping force that we've added. To make this look more mathematical, what I'm going to do is I'm going to put this d squared x over t squared plus gamma dx over dt is going to be equal to q e naught over m times cosine of omega t. Again, the way that we would solve this is we'd usually first do the homogeneous part where we set this side equal to 0. What we'd do if we did that is we'd find that x of t would have some unknown constant times the exponential of minus gamma t or something like that. And then there'd be another one that's linear, also damped, bt e to the minus gamma t, like that. So those are the two solutions that you'd find. Again, we're going to ignore these. We're going to set them equal to 0. These we can very justifiably set equal to 0 because we say that if we wait long enough, where long enough is simply a few of these gamma times, if we wait long enough, then this problem will go to 0. This solution will go to 0, and so we can ignore it. What we're looking for is the driven solution, the solution from the driven part of this. And so to do that, we're going to have to make an assumption. We're going to make an assumption that this x has sines and cosines. So a cosine omega t plus b sine of omega t. We then take that assumption that we made, that ansatz, and we plug it into the differential equation right above, and the second derivative right is going to give minus omega squared a cosine omega t minus omega squared b sine omega t plus gamma times minus omega a sine omega t plus omega b cosine omega t. Whole thing equals q e naught over m times cosine of omega t. What we do is we now gather the cosines and the sines into two separate equations, and we drop them, and so we get minus omega squared a, that's a cosine, plus gamma omega b, that's a cosine, is equal to q e naught over m. And then for the sines, we get minus omega squared b, and then minus omega gamma a is equal to 0. This isn't too bad for us. This is actually pretty nice. We can say b, right, is going to be equal to minus sign here, I believe. When we pull that to the other side, we get positive, but then when we divide by the minus omega squared, we get minus again, gamma over omega a, like that. So we're going to plug that back in over here, and we get minus omega squared minus gamma squared a is equal to q e naught over m. Finally, the amplitude here is equal to q e naught over m 1 minus q e naught over m 1 over omega squared plus gamma squared. That's fine. Now I'm actually going to plug this directly back into the x dot, or the velocity term, and I'm going to also use that substitution for a moment. When I take the derivative of the cosine, I get minus sine, so this gives me q e naught over m 1 over omega squared plus gamma squared, and so I get a omega sine of omega t here for the x, and I I get a minus gamma cosine, the gamma because I have an omega over gamma here, and a minus sign from there, cosine of omega t. And that's it. So now I need to plug in what we had before. And at this point I need to go back and do a correction to what we did up here. And so this part right here is missing something. This b also has a cosine of omega t in there. And so there's a cosine of omega t still in here. And so this is what goes to 0. Sine times cosine integrated from over one period still goes to 0. And so there's a correction there that I needed to put in. And so go ahead and do that. Then we come back to here, and we can see how this is going to factor out. The magnetic force is going to have our Q E0 over C. That's from the QB. And then we have Q E0 over M. That's from this term. We have a 1 over omega squared plus gamma squared. And now we have something interesting. Now we are going to have omega sine of omega t cosine of omega t. The sine is from the x, the cosine is from the magnetic field, minus gamma cosine squared of omega t. Now when we take the time average, okay, the time average, this goes to 0, but the time average of cosine squared is a half. And so the time average of the magnetic force for this damped system is Q squared E0 squared over MC gamma over omega squared 2MC, so 1/2 there, gamma squared. And so if we have a some substance that has damping, there will be a non-zero average magnetic force from that substance that has damping. And that's how you can transfer momentum from light into something like a crystal, where the crystal are going to have atoms that can vibrate back and forth. There'll be some damping factor there, and so that's a way that you can have light come through, excite those, and transfer some of the momentum into the crystal. Yay!